Very good morning. Let us have the next lecture, that is the lecture number 6 in the same unit on the topic of theory of relativity, that is in the relativistic mechanics. Here in this lecture I will take the effect of velocity on the variation of mass. As already this has been discussed in the last term, that is, if we are moving with very fast velocity, then the mass remains no longer constant and that will vary in according to this expression. This change in mass will lead to the change in energy also, and how that can be discussed and how corresponding value of energy we can calculate, that we will discuss in this lecture. Is that if the mass is changing, then corresponding to that change in mass may appear in the form of energy, that is delta M is related to the energy that we have to discuss in this lecture. We have to derive the relation between the change in mass corresponding to the energy. That has been derived and suggested by Einstein himself. That important relation is known as mass energy equivalence. Mass energy equivalence. Equivalence means mass will change into energy. This is so important that it is also known as the scientific signature of the great scientist Einstein. According to this expression, we will see that E is equal to delta M into C square. This delta M will be equal to M minus M0 multiplied by C square. This will be the, we have to establish this relation. Then after, we have to also discuss that what are the massless particles, and if we have this change in mass and corresponding to change in mass, we may have certain relation between the mass and energy. Using these relations, we may have the so many consequences also. Means anybody may ask that is there any experimental verification of this one, that we have to discuss. That is experimental verification of mass energy equivalence. Experimental verification. At the same time, we have to also discuss, anyhow it may happen that the mass of a body becomes zero, that is the massless particle, or the rest mass of a body is zero. Rest mass of body is zero, thus M0 is zero. What is the interpretation of massless particles? What are the massless particles? In the limelight of the variation of mass, how the Newton's second law will change, that we have also discussed in this lecture. Relativistic form of Newton's second law. Also we will see what are the relativistic momentum and energy, and how they are related to each other. Means that relation between relativistic energy and momentum. All these topics we have to discuss in this lecture. Before starting the discussion on the topics which I have mentioned here, let us see this famous statement of Einstein, that essentially it is required to have a balance in our life, and for that we can compare our life with the riding of a bicycle. Till we are riding the bicycle is in motion, then we are safe. But as soon as we will stop riding of the bicycle, then we will fall. So that has been stated by the great scientist Einstein. I like post this statement. Life is like riding a bicycle. To keep your balance, you must keep moving. If you will stop, then definitely you will fall. Till you are in motion, you will be safe. So here we have also the relevance of this particular statement. If we are in motion, and that is of high speed, then only we will be safe in the relativistic mechanics. Otherwise, we will fall in the classical mechanics. Means if the velocity of a body will reduce, then we will go to the other dimension of other region of the physics, that is the classical mechanics, and the relativistic mechanics will be left there. Let us see that what is the mass energy equivalence. It is the great equation derived by Einstein, and you will be surprised to know that all the atomic bombs as well as the interpretation where the binding energy is required to be in nucleus for the particle, all these interpretation can be done with the help of this relation, that the total energy E of a body is equal to rest mass energy plus the relativistic kinetic energy. This we have to always remember in case of relativistic mechanics. Here the relativistic kinetic energy has been mentioned, that is different from the kinetic energy whatever we have read in case of classical mechanics. Slightly that will be different, and you will see from this expression also that it is not half mv square what we have enjoyed in case of classical mechanics. Rather, it is equal to m minus m0 into c square. Means the change in mass of a body due to its high speed is responsible for the relativistic kinetic energy of that body, that we will see in this expression. So, what the fundamental statement has been given for this one? Mass energy equation is the most important significant relationship derived by the Einstein from the postulates of his special theory of relativity. This relation is also known as the scientific signature of Einstein. According to this relation, we will have this expression. Now we have to derive this equation. In order to derive this equation, we will start from very basic thing or very basic or fundamental concept. In that concept, what we are considering, that is very simple, that we have a particular body. Although whenever we draw this type of picture, then always the sense reflects that we are in classical mechanics. But anyhow, we have to think that we are not in classical mechanics. This particle is ready to move in the relativistic mechanics. That's why it may acquire the maximum velocity in comparison to the velocity what we talked in case of classical mechanics. So if we wish to have the velocity of this particle, then definitely we have to apply a force on this particular particle. Under the action of this force, some work done will be there, and that work done will appear in form of a kinetic energy. As usual, what the basic laws says for that, what the basic law state for the same. So here if we are applying the force F, then it will be displaced by a certain displacement. Let that displacement is dx. Then the work done, that is dw, displacing this body in the direction of the force, that will be equal to F dot dx. This will be the work done on this body. Corresponding to this work done, how much kinetic energy will be there? How much kinetic energy? Why I am talking about the kinetic energy only? Why not for the potential energy. As usual, we have seen in the case, such cases in the classical mechanics, we always used to have the part of kinetic energy as well as the potential energy. But here we are taking care of the kinetic energy only. Reason is what? Reason is that when force has been applied, then it has been assumed that the particle started its journey of motion with the tremendous velocity. Means that no static situation is there. No the situation we can compare to contribute the potential energy for that particle. Since it has started to move with the high speed, that's why all the energy or the work done on the particle will appear as a kinetic energy. That's why this dW, it means that the work done on that particle, this dW will be equal to dk, and this dk will be equal to F dot dx in this way. Now the change will start from this force, because this displacement is only because of the force applied to that particle. That's why for entire change in that body, which will reform that body from one state to the other state, leading to a kinetic energy or contributing a kinetic energy to that particle. That's why F should be taken into the care. F is equal to d by dt of the P, as usual what we have read in case of classical mechanics. Now you may say that why I am using the expression of classical mechanics. The laws of the physics remains invariant in all inertial frame of reference. But when we are extending the laws of classical mechanics to the relativistic mechanics, difference is only this one. If the particle will move with the tremendous velocity, it never means that the principle of the classical mechanics will not be applicable in case of relativistic mechanics. They may be subject to the condition, or the provided they should be considered with the high speed. Means that the factor or the parameter or the terms involved in that expression having the velocity component, that should have its value very high, and that should be comparable to the velocity of light. Only this is the difference between the classical mechanics and the relativistic mechanics. Here we are taking d by dt of P multiplied by dx. Here we are taking this one. Means rate of change of momentum. Rate of change of momentum is known as the force according to the Newton's second law. Here if we are taking d by dt of P, and this P is no longer remains as m0 v r, m is constant and v is not like that. Here we'll have P is equal to m into v, and here v is the variable as usual. It is in case of classical mechanics. But in classical mechanics, this m has been taken as a constant quantity, that is the inertia of a body. But here this m is not constant, but this is the variable. Now this will be the product of two variables which we wish to differentiate with respect to the time t, and here differential part means that dx part is there at outside, and here we will write that dk that is equal to dw, means the work done because of a force applied on the body. Here if m is the variable, then we will write it as first function differentiation of second plus second function differentiation of first one in this way, and this will be dx as such we have taken it. Now what we can write here, we may write it as by introducing this dx inside the bracket, m dv into dx upon dt we can write, plus here again we can write v dv dx upon dt multiplied by dm, in this way we can write. here dx upon dt and here dx upon dt. This is the change in displacement with respect to time. Obviously, that will be velocity. So we will write it as mv dv, and here we will have v square dm. This will be the value of dek, what we have obtained due to the variation of mass, due to the consideration that mass of a body remains no longer constant. It will vary with respect to its velocity. How the velocity is changing, according to that it will change. Now let us have the next discussion related to the same topic. That now we have taken f is equal to d by dt of md, and that is equal to this one what already I have discussed here, and by doing we have reached to this point that mb db plus v square dm. Now let us take how the mass of a body is varying. Mass of the body is varying. Mass of the body is varying. For that we have the expression that m is equal to m0 upon under root 1 minus v square upon c square. Let us have some mathematical manipulation on this expression. By doing this, we can write m square, this is equal to m0 square divided by c square minus v square, and c square was in the denominator. Let us write it as here c square. So here c square, m square, m0 square, c square upon c square v square. Let us have the multiplication of this m square with this term by cross multiplication. We have this expression. Already you will see from this expression that m square c square minus v square is equal to m0 square c square. Now we are going to differentiate it. And again we will consider that mass of the body remains no longer constant. That's why we have, let us expand this bracket, then it will be more clear and better. M square c square minus m square v square, this is equal to m0 square c square. If we will write it in differential form, then first we will have this term. So obviously this c square is constant because the velocity of light is constant. It has nothing to do with the position of source and observer. It will be constant. If it will be constant, then we have to differentiate only this part, and we will have 2m dm, and c square will be here. So 2m c square dm minus this this particular term is the product of m as well as of v. Here m is variable as well as v is variable. That's why we will take care of both the terms when we will differentiate this equation. And it will have first term is m square, differentiation of second, that is 2v dv. This is, now again we will have plus means here minus sign is here. That's why we will write 2m dm multiplied by v square. And here at the right hand side we have m0 square c square. m0 square is a constant and c square is constant. That's why we will put it as a 0 when we will have the differential form of the right hand side term. Here you will see that in this entire expression 2m is common throughout the expression. and since right hand side is 0, that's why 2m can be eliminated from the entire expression. And here we will have c square dm minus 2m means mv dv, and here minus 2m will be eliminated. So here we have v square dm, and this is equal to 0. We can write it as c square dm, c square dm. This will be equal to the rest of the term at the right hand side, mv dv plus v square dm. This will be. Let it is equation number 2, sorry, because already we have equation number 1, which we have obtained by the differentiation of the m and v, which was for the momentum of the particle, and that equation already we have seen in the last slide. Here let us see what the expression we got for that. Here this expression, that dk is equal to mv dv plus v square dm. This was equation number 1. If we will compare equation number 1 and 2, then you will see that the right hand side of both the equation is same. That's why the left hand side will be same, and hence we can write dk is equal to c square dm. This will be the equation. And if we are having this equation, that is dk is equal to c square dm, and we can integrate this equation for the total energy, how the energy is changing and how mass is changing according to that energy, that kinetic energy. And kinetic energy means that how the velocity is changing, or velocity is leading to the kinetic energy, and how this velocity is affecting to the mass of a body. So if we will do it, then we are considering that in the start of very beginning our particle was at rest. If particle was at rest, then we will say that the kinetic energy is 0. And last stage means that next stage, when it has been force has been applied to the particle, then it will be k, for example, and this will be equal to dk. Dk is changing from 0 to k, and it will lead to a change in the mass of a body is starting from m0. M0 is the rest mass when particle was at rest, and it has a certain mass, that is the varied mass of the particle, that has been equal to m, and here we will have dm. If we will write the value of this after getting the integration, after solving the integration, a definite integral on the both the sides, then you will see that this is k. K means kinetic energy. Better to write it as ke, that is the kinetic energy, and this will be equal to c square, here multiplied, and here we will write the higher limit means m, and here we will write the lower limit, that is m0. This is equal to m minus m0, and hence the kinetic energy will be equal to delta m into c square. This is the expression what has been derived by the Einstein as mass energy equivalence. At the same time, one thing is very important also, as we are talking about the kinetic energy of the particle only, but similar to the potential energy what we have discussed in case of classical mechanics, what will be there in the relativistic mechanics, and there is the concept corresponding to the same energy as we have enjoyed as the potential energy in case of classical mechanics. Here we have rest mass energy, means that the energy of the particle due to its rest mass, so that is equal to m0, and with the analogy of this one, that will be equal to c square. So this is known as the rest mass. rest mass energy. Rest mass energy. So this rest mass energy is equal to m0 into c square, and the kinetic energy of the particle under the action of the force, which will have the momentum on that particle P, will have this value of the kinetic energy. Hence we can write the expression for the total energy of the body also. For the total energy, we can write here total energy E is equal to the rest mass energy, rest mass energy plus kinetic energy. By putting the values, we'll have m0 c square plus c square multiplied by m minus m0. Now you will see that m0 you can write it as in the extended form, m0 c square plus mc square minus m0 c square. These two will cancel each other, and finally the total energy E total will be equal to mc square. This is again termed as the scientific signature of the great scientist Einstein. But you will see that I have tried to derive this one and this expression. You will see finally we are getting k is equal to c square multiplied by m minus m0. From this discussion you will see from the expression of kinetic energy, it is clear the increment in the kinetic energy is due to the increment in the mass of a body on account of its relative motion, and m0 is known as a rest mass energy, which may be considered as the internal stored energy of the particle. It's very important, and that will give the same significance and same type of essence as we have seen the potential energy in case of the classical mechanics. Yet hence the total energy of a moving particle is the sum of kinetic energy and its energy at a rest. So for that we'll have the expression here. The total energy is equal to rest mass energy plus relativistic kinetic energy. This is relativistic kinetic energy what we have written here. This is not only the kinetic energy, because if you are talking it as a kinetic energy, you will say that it is kinetic energy in the relativistic domain, or simply it will be better if we will write it as a relativistic kinetic energy. Otherwise people may ask that kinetic energy of the classical mechanics also, but here this is relativistic kinetic energy, and hence m0 c square plus m0 minus m0 into c square, and finally E is equal to mc square. The above relation is the well known Einstein mass energy relation or mass energy equivalence. Now let us have some experimental verification, but before discussing that experimental verification, it is very important to discuss about mass energy equivalence, that the energy will change as the motion of the body will be there. If speed of the body will be more, then obviously kinetic energy will be more, and hence we will have the more value of the total energy. Here if we will try to discuss the experimental verification of mass energy equivalence, then first evidence flashes in our mind, that is electron-positron pair annihilation and electron-positron pair production. In this pair annihilation, what is happening, if we have electron with the negative sign here and we have positron with a positive sign, if they both are combining with each other, then we will have only the energy. Before combining, these two have a particular mass, and that mass has been disappeared, and here we have the energy only. Here we will have the photons of particular energy or frequency. So this is first example, and its counterpart is also there. Sometimes what happens, electron and positron pairs are produced by the energy, means energy has been converted into the mass. So these two evidences are the direct proof of mass energy equivalence. One example. Next we will have, just we have taken this particular gamma radiation is there, that is the photon of a particular frequency. Here if we have the gamma radiation energy that may produce the positron as well as the electron, and finally this is termed as the conversion of energy into the mass. The mass energy relation forms the basis for better understanding of the nuclear phenomena like nuclear reaction such as fission and fusion. The phenomena of nuclear fission as well as of fusion can be also explained on the basis of mass energy equivalence. The most important example what you will see here, the tremendous energy produced during the explosion of the atomic bomb is due to the conversion of mass into energy according to this relation. And one more example, what I remember that sometimes we will see that inside the nucleus, if we have inside the nucleus here, it is nucleus and here some particles are there, then this nucleus is not stable at all. It is not static. Certain particle and exchange of the particle are taking place always there. And if anyhow in a rough sketch we are considering what is inside the nucleus, then we used to say that proton is there as well as the neutron is there. Proton and neutron is there. If proton and neutron are lying here, then some binding energy will be required for that, and that binding energy can be given by the mass defect of this nucleus. Mass defect means that if we will count the mass of individual proton and mass of individual neutrons and we will sum up there, then their sum will be always greater than the mass of this nucleus, means that change in mass, difference in mass will appear in form of energy, and that energy will be used to bind the proton and neutron in the nucleus. So this is also one example of the mass energy equivalence. On the basis of the relativistic term is, if we are considering the relativistic form of mass of a body, then it will affect the momentum of the body, it will affect the energy of the body. That's why the relation between the energy and momentum will be slightly changed in according to the variation in the mass of the body, and that we are going to discuss here, how the relation can be established between momentum and energy by considering the relativistic mass of the body. So the expression of relativistic total energy of a particle moving with the velocity v is given by E is equal to mc square. Well, already we have discussed this one. If E is the total energy of the particle and m is the varied mass, c is the velocity of light, so E is equal to mc square. For just a moment before I discuss here, I have discussed there. Kinetic energy will be equal to m minus m0 multiplied by c square, and if we are including the rest mass energy of the body in the with that energy, then we will get the total energy, and finally that total energy was equal to E is equal to mc square. Now this m is the mass of a body and having its high dependence on the speed of the particle. That's why in place of this m we may write it as m0 upon under root 1 minus v square upon c square, and here we will write E is equal to m0 upon under root 1 minus v square upon c square into c square, and here m0 have its usual sense, that is rest mass of the particle. Here if we are writing that E, just we are taking this first equation, E is equal to m into c square. Better to do it, then that will be the better practice to you people as well as me also. And E is equal to m into c square. E is equal to m0 upon under root 1 minus v square upon c square into c square. If we will square both the sides, then it will be equal to E square, and this is equal to m0 square c to the power 4, and here we will have c square minus v square, c square minus v square upon c square. Let us multiply it by c square, then we will have E square multiplied by either this we are writing 1 minus v square upon c square, and this will be equal to m0 square into c to the power 4. You will have this way. So here if we will open the bracket, then E square minus E square v square upon c square, this is equal to m0 square c to the power 4. This will be the way. Or simply we can write this E square is equal to E square v square upon c square plus m0 square c to the power 4. This is the relation between E and V. Now we may have some exercise with this one, with V, because still in this equation, in this entire expression, we don't have the appearance of P. So that's why we have to introduce P here. And for that, for P, what we will do, if we have V there, then P is equal to mV. And if we are writing P square upon V square upon m square, then it will be corresponding to V square. In place of V square, we can introduce this one. So here we will write E square is equal to E square multiplied by P square upon m square into c square, and here we will have m0 square c to the power 4. E is equal to what? E is equal to what? This here, you will write this term, this entire term, then it will corresponding to the P square C square, and here plus m0 square c to the power 4, and this is equal to E square, and this will be the. How we got this one? You will see here. E is equal to what? E is equal to mc square. How we got it? E is equal to mc square. If we will square this one, then E square is equal to m square c to the power 4. Means here we need c to the power 4. So for that, c square must be multiplied here. So if we will multiply here c square, here c square, then E square upon m square c to the power 4, and these two will be cancelled out. Here P square C square will be there. And finally, what we will write for the expression of E only. So either you are writing it as E square is equal to P square C square and 0 square C to the power 4, or by taking the root on both the sides, we may write it as under root P square C square plus M0 square C to the power 4. This is known as the relativistic relation between the energy and momentum. Means if we have taken the relativistic form of energy and momentum, how they are related to each other. That expression we can write in this part or whatever we have written here. Here expression of relativistic momentum. There is no much change in the relativistic momentum. Only the change is here. If we are writing P is equal to mv, then v is the velocity by which the particle has been accelerated, and in this sense P will be equal to m into v, but under the velocity v, this m remains no longer constant. However, it will vary with the velocity v. So we will write here P is equal to m0 upon under root 1 minus v square upon c square, and here v will be there. This is known as the relativistic form of the momentum of a particular particle. Now let us have the discussion on some more topics. Relativistic form of Newton's second law. This is very important. This is very important. Why? This gives the direct reflection how the classical sense of the Newton's second law changes when it has been considered in the relativistic mechanics. How the form of that law will change. So for that we will start from the basic and fundamental concept what we have read in the classical mechanics. What is in classical mechanics? According to the classical mechanics, we know the statement of Newton's second law. Do you remember? Yes, you might remember it. That according to the second law of Newton, the rate of change of momentum is known as the force. So here we are writing that F is equal to d by dt of P, where P is the momentum. And already in the start of very beginning of the today's lecture, when we were started our discussion on the mass energy equivalence, there we have taken F is equal to rate of change of momentum, where momentum is the product of m and v, while both are variable. As in case of classical mechanics, we have taken that m is constant, that is the inertia of the body, and v is the variable, but here both will be variable because the mass of a body remains no longer constant while it is varying with the velocity. That's why we will take the sense of this expression that F is equal to rate of change of momentum. Here relativistic momentum we have already discussed just a moment before. That's why we will write it as F is equal to d by dt of m0 as well as of v divided by under root 1 minus v square upon c square. This will be the value. Now again we have the product of two functions here. Two functions means m0 upon under root 1 minus v square upon c square, and here v square. Both will be treated as two functions which are variable with respect to time. That's why we will differentiate it with respect to time by considering this particular bracket quantities as a product of two functions. Here we will write the differentiation of first function multiplied first function means that m0 upon under root 1 minus v square upon c square multiplied by dv upon dt. First function differentiation of second, and here when we will take the a second function, that is v, and differentiation of first. So here m0 is constant, only this term will be here, and it have the negative power of negative half power of this expression. That's why we write minus half, and this bracket will be 1 minus v square upon c square whole to the power minus 3 by 2, and again this quantity should be differentiated. That's why we will have 2 times v dv upon dt, and here upon c square will be there because c is a constant quantity. So this will be. When we will solve this, then this 2 and 2 will cancel out, and if we will take this quantity, this 1 minus v square upon c square to the power minus 3 by 2 as a common, then we'll have the expression in this way what already have written here, that d by dt of m0v upon this one. Here we have taken v into 1 minus v square upon c square as a variable, and both one has been differentiated. Then we have taken m0 as a common and dv upon dt as a common. So you will see here what we will get, because that has been written directly. Better to see it how we are getting this one. So here m0 is a constant that we have as outside, and dv upon dt it is common, and we are deliberately taking 1 minus v square upon c square whole to the power minus 3 by 2 as a constant, as a common. Then here what we will get, m0 has been taken as outside, dv upon dt has been taken as outside, and here only 1 minus v square upon c square to the power minus half is prevailing. That's why we will have a multiplication of a term 1 minus v square upon c square here, and here we have taken this v, and here we have taken here 1 minus v square upon c square we have taken, and here this minus sign is prevailing here, and if we will take this entire term as a common, and here we have v upon c square, then one negative sign will be again here, because this is minus v square upon c square. That's why minus sign will be here, and this minus sign and this minus sign will be the positive sign, and here v is there, and this entire term has been taken as a common. That's why v square upon c square, and this dv upon dt has been taken as a common. So inside the bracket what we will have, finally we will have, by taking all the things as a common, v square upon c square, v square due to this v and this v, minus will be plus due to this minus, this already has been taken as a common here, and this has been taken as a common. That's why we will have v square upon c square here, and finally these two will cancel out, and we will have the form of relativistic Newton's second law, that is m0 dv upon dt 1 minus v square upon c square whole to the power minus 3 by 2. This is known as a force. According to the Newton's second law when it is applied in the relativistic mechanics. Some more important topic which I wish to discuss, that what is the basic concept related to the massless particle. How we can explain the massless particle, and what is the concept of this massless particle. Massless particle are those particles which have no rest mass. When they are at a static condition, they bear zero mass. They will have the mass as long as they are in motion. So that's why we are explaining here. The particle having the zero rest mass are known as the massless particle. The existence of massless particle is beyond the scope of classical mechanics. Means in the classical mechanics we never have the sense of zero rest mass or massless particle. They will have a certain mass when they will be static, that is the inertia of the body. And when they will in motion, then it doesn't matter that how their mass will change with the velocity, because it is the task which has been considered only the relativistic mechanics having the high velocity of the motion of the particle. But according to the relativistic mechanics, the particle with zero rest mass may exist. The energy and momentum of such particle can be calculated with the expression of relativistic total energy, which is given as E is equal to under root m0 square c to the power 4 plus p square c square. Already we have derived it just a moment before. And if we are writing that m0 is 0, m0 is 0, then what will happen with this expression? That E is equal to, this part will be 0, and here finally we will have p square c square. By taking the root of this one, we will like P is equal to energy divided by c. Means always remember that the particle have the momentum also, even they have zero rest mass, and they are massless particle in its static condition. Even then they will have the mass as well as the momentum when they will be in the state of motion. So massless particle and their explanation, that since P is also equal to the mv, and this mv is equal to E upon c square into v, because m is equal to E upon c square. So therefore v is equal to c, that is the velocity of massless particle is the same as of the light in free space. Massless particles are usually found when they are moving with the highest velocity, that is approaching to the velocity of light. It indicates that massless particle has mass as long as it is in motion. On being stopped, they cease it to exist. They are either absorbed completely or changed into the heat at the surface. Example of the massless particle are usually this photon, neutrinos and gravitons. A particle which has its rest mass 0 and has its mass during its motion can be explained on the basis of the expression of the variation of mass, that is m is equal to m0 upon under root 1 minus v square upon c square. Actually during the motion of the particle, the energy is converted into the mass, and it is also known as the materialization of energy, that is the conversion of the energy into the matter. This is the most important fact what I have concluded at the last point, that when particle is in motion, then energy has been converted into the matter. That's why the body becomes heavier when it is in motion, and that can be justified with the help of the expression that m is equal to m0 upon under root 1 minus v square upon c square. This theory is known as the materialization of the energy. So here we have some more points we have to discuss. Only as a summary we can see here, the moving clock runs so slow, moving object appears shorter, moving object mass increases by a particular factor, that is gamma equal to 1 upon under root 1 minus v square upon c square. Here as far as assignment is concerned, we should always examine that what we have learned after this lecture, and in this you should always practice to the questions which I used to write at the end of all the lectures as assignment questions. Here first is obtain the expression of mass energy equivalence. Already I have discussed this one in the first point. Describe how the kinetic energy and the total energy have the different sense in the relativistic and classical mechanics. We have to compare it, how if we are changing the velocity, then how we are reducing the domain from the relativistic mechanics to the classical mechanics. Give the experimental evidences in the support of the mass energy equivalence. Already we have given positron and electron, which pair production and pair annihilation. Establish the relation between the energy and momentum, that is the relativistic relation between the energy and momentum. Obtain the relativistic form of Newton's second law. Explain the existence of massless particles. So this is all about our today's lecture. We will meet next day in the next lecture.